Hey you guys, so I'm going to give you some more of that review in pieces. This is number 14, and I think that's the one that you might get stumped the most, and it relates to one that's on your take-home test as well, so hang out here. So this is Chapter 7 review, part 2. Now the problem is, oh by the way, I'm going to do number 15 really fast too. Should have told you. The answer to number 15 is D. It's circled down here for you. And that's test 2 and 3 only. And if you guys remember, take a look at the notes we took the other day on the table values. This is saying that I get my next y value here from taking the y value before, that's y1. So y2, the next one, comes from y1. And you add dy dx times delta x to that to get the actual value. Now if you remember what that means, f of x of y, if you look up in your original here, it says that's the same thing as dy dx, and we're multiplying it times delta x dx, which is change in x. Just do the arithmetic here with me. Di dx times dx. Do you see that these cancels, and that just gives me dy? So by adding this little function here on the end to y1, we get the change in y dy necessary to get us to y2, the value we're looking for. So that's just the general kind of equation that goes with finding y2. And then number 3, the next x value, or the third x value, comes from taking 3 iterations of delta x added onto the original x value. So those are the 2 true statements in there. Go ahead and run with that. Now as for number 14, let's keep rolling here. I'm going to go on to, let's see if I can find it in my notes. I've got some stuff rolling here. Oh, I had it on here. I must have deleted. Hang on just a second, I'll pause and I'll pull that up for you guys. Okay, so here's this next piece. 14, this was the kicker. Now it gives you the function for slowing to a stop. By the way, you're hearing Graham, he's home again, and he's kind of singing in the back there. Maybe crying in a minute too, I'll get him. But here is that function. Basically, this is your initial velocity, v0, and it tells you k is your constant, and it gives it to us in the function 80. And then m is the mass of the vehicle, 1200. I think it's kilograms. I'll have to look back at the original. But those are the pieces, and velocity is measured velocity in a given moment. So if I get rid of those little markings here, that's the function we're working with. The first question is, how long until you come to a complete stop? Well, there's a big counterintuitive piece to this. That would mean velocity equal to 0, right? Well, if you try and set this equal to 0, this original function here, it's not going to happen. If you graph it, it's like any exponential decay function. The negative here tells me it looks like what you see to the right circled, and that function always is positive. As time goes to infinity, it approaches 0, but it never actually gets there. So we can't just set it equal to 0. That doesn't work. So here's what we can do, and this one takes some funny intuition, and I have a little note at the bottom of this. I'll show you here in a minute. Basically, this problem seems counterintuitive, but what we're going to do is we're going to integrate the position, this velocity function. So here it is. See that original? What if I put in all the values that were given? Take a little arrow down here. This is what it would look like. Okay, there's your 20 initial. Part A says if I start at 20 kilometers per second, how long until I come to a stop? So the 20 is v0, and then the 80 and the 1200 are the 2 other givens. I have to go to infinity on time in order to find out when this thing comes to a halt. Now that sounds strange, doesn't it? The time going to infinity takes this function I just circled in blue here and shows me when it goes to 0. I have to go t to infinity just to find out when velocity is 0. So that's the big key. I'm going to go limit t to infinity is how I'm going to find out velocity equal to 0. So by doing that, it seems really counterintuitive, time going on forever, but we're going to find it. It's a good thing. So I need to, but the question's about how far does it travel, this object or car or whatever it is, it's a car, when it comes to a halt. How far does it travel when it comes to a halt? Well, we know that time going to infinity is how we get velocity equal to 0. I'd like to know how far the car travels, how far it's displaced in that event. So what we're going to do is take the integral of the velocity function, which gives us displacement, for any interval of time we want. Well, the time I want is 0 to infinity, because that's when the car comes to a stop. So I'm integrating from 0 to infinity of velocity to get displacement of the vehicle on the interval 0 to infinity. Sounds kind of counterintuitive, like I was telling you. But watch what happens. The integral works out pretty well. And I know this is a little bit small, but if you can imagine, remember we're taking the integral of e to some function linear function up here, then we can just have the inverse of the derivative ends up out front here. So that's, instead of 80 over 1200, that's 1200 over 80, and it's negative. The 20 is the v naught carried over. And then you rewrite the original function. Okay, so that's antiderivative of e to some at. We got it there. Now, we put in the infinity and 0, which I did below. If I put in infinity into that function, we know that if we do e to that function, e to the negative 80 over 1200t, that as you go to infinity, that actually makes the function equal to 0. That's a good knowledgeable piece. So any exponential decay as you go to infinity goes to 0. So that first function is 0. And then the second one, we're putting in 0, which is good too, because e to the 0 is 1. So that means we just get these coefficients out front here for that second piece. Okay. Now you evaluate those, you get 300. There's our answer. It takes 300 meters for this object to come to a halt. The work isn't hard. You just take the antiderivative of the velocity function on the interval 0 to infinity, because we're trying to find out when it comes to a stop, which is at time equals infinity. Interestingly enough, we get an actual displacement amount. So I'm going to go through the concepts here in the next piece just to kind of, set it straight. So let me get to a nice, clean, new sheet, and I'm going to bring in the picture again, so just bear with me. And let's see, photo stream, working in real time with you guys. Okay, here's what I just finished with. Here are the big concepts I was going on. Yep, there's Graham again. The piece here, we needed displacement, or how far s of t moved on the interval 0 to infinity, because that's when we know velocity actually does go to 0. This is the counterintuitive part I boxed to the right. The idea that time goes to infinity because the object actually never stops. You have to keep, objects have velocity with, we have this resistance piece, but by the function it looks like the velocity never actually hits 0, it's always moving. Yet displacement is fixed. The object actually does only move a fixed amount of distance. It's just as you're moving smaller and smaller increments of distance in that time, it becomes negligible, and we actually only move 300 meters. And so that's wild. So anyway, you might want to ponder that problem for a while. That's 14 and 15 for you. I'll do 16 in another video here pretty soon. Email with questions.